Welcome back. All right, in this particular week, we're going to give you the opportunity to develop some meaning for our remaining two operations. That's multiplication and division. And of course, if you remember the way we described that last week, because these two are inverses, where one undoes the action of the other, we can treat them as if they're a single operation for the purpose of instruction. This turns out to have some great impact when we think about how to present them, because just like we can teach addition, subtraction at the same time, we can also teach multiplication, division at the same time. So when we start thinking about multiplication and division, there's a few thoughts that I want to share with you to kind of supplement what your readings from Vonderval should have shown to you. Let me again encourage you to keep up with those readings, because they're going to have a lot of information that will help you in terms of making classroom sense out of a lot of this, together with some wonderful ideas and implementation strategies. Our next two formal operations have to do with multiplication and division. And of course, we're referring to operation on number rather than Piagetian operations. The nice thing about these operations is, just like addition and subtraction, they are very easily modeled using action upon objects. And we'll spend a little bit of time doing that. To help us picture this, I'd like us to go back and just review for just a moment what our learning model would say about it. First of all, you'll notice that we're going to be using manipulatives in our discussion for today. Manipulatives are the appropriate object for us to act upon, particularly for early childhood through maybe 3rd or 4th grade. When we hit sketching, as I'll demonstrate for you when we talk about fractions and rational number, sketching generally is not until 4th through 5th grade. And by 6th, it's fair game. 4th and 5th is maybe, maybe not, all right? Now, in our teaching cycle, the first thing that we do is we generate vocabulary. And so when we think about memory recall in this case, remember the story of the fuchsia tray. We're just talking about enough vocabulary. So if I ask a young child to do something, to select the hundreds block, for example, they'll have sufficient background and understanding to where they'll have the appropriate object selected for us to work with. The one exception for this is going to be number itself, because remember, we've developed numerical fluency. So I can use an abstract symbol, but because we understand the symbol to object to word relationship from numerical fluency, when we use that symbol to represent number, it still has that physical object connection. So we can use symbol to record our actions upon physical objects. We didn't really stress that overly much, but that's certainly an important part of the learning approach. Now, once we have enough vocabulary where we can work with our students, as teacher, we pose a problem that involves activity, organization, and finally, the creation of a record of action. And remember, if we do our job right, the record of action is the formal procedure. So we can send that home just like we did with the subtraction, the comparison, the addition problems, and we can get that family support. Again, we're going to try and do the same thing for each of our operations and each of our types of number, whether it's whole number, whether it's fraction, whether it's decimal. We want the record of action to look like the final work that the kids would see on a very traditional textbook or a traditional worksheet. This actually makes quite a bit of sense. Lancelot Hogben wrote an absolutely wonderful book called Mathematics for the Million, where he talks about how 99% of what most people think mathematics is an accident of notation. And so the record of action is this notation. And so we have to make sure that our record looks like the records that are used in the mathematical community at large, as well as the culture the students are going to be going back into. By the way, think back on Pa Kettle, the way they showed division with a symbol here and a symbol here, much different than what we use today, but that was certainly appropriate at the time that that little video was shot initially. Now, when we think about self-posed problems, to me, this is an absolutely wonderful thing to include if you can, because it gives the students a chance to show they can be mathematicians too, that they can select a good problem that's meaningful for them, that they can select an appropriate activity, typically borrowing the same type of activity that we have done with them and demonstrated and helped them develop, that they know how to organize their work, and again, along the lines of what was modeled for them, and that the record of action they generate corresponds to the type of record of action that we would expect to see in a textbook or in a worksheet. Now, as we go through our examples today in multiplication and division, I'd like you to try and decide where in our model each step would fit. So I'm going to encourage you to get another copy of that action on objects sheet, just so that you can be going through this process and saying, okay, what is it we're doing? Are we building vocabulary? Are we posing a problem? Are we having an activity? Are we organizing the activity? Are we building a record? This will give you practice in terms of using the action on objects in design of instruction. It's only fair to tell you that in our local area and in most of the textbooks you're going to see in the schools, you're going to see multiplication represented in probably one of three different ways. So I want to illustrate each of those for you. You're going to see it as repeated addition on the number line. You'll see it as groups of items, and I'll call this the stars and circles model. This particular model is the model that Teach for America used in the past. If you've ever been in a Teach for America classroom, you've probably seen this model at use. And finally, the probably most powerful model is that of the area model. And I'm very certain that you'll see why it's going to be the model of choice once we develop this. So let's take a look. Here's repeated addition on the number line. Let's see what we've got. In this approach, we have a number line, and it's used to record the distance that a given number of equal jumps covers. And sometimes I call this the Freddy the Frog problem. Way back in the steps days, which came before the toss, which came before the star, I mean, this is several state tests back, there was a problem about Freddy the Frog, and it said Freddy the Frog always jumps 3 spaces. If Freddy jumps 3 times, how far will he go? And what's interesting to me is here it is almost 30 years later, and we still see Freddy the Frog-like problems show up in curriculum, and shows up in teachers' guides, and shows up in a lot of the district and services that you'll see. So let's go ahead and let's build Freddy the Frog here and take a look at what's happening. There's Freddy. He's showed up finally. And when we look at Freddy, we're going to notice what happens. Now think what's going to happen the first time he jumps. From the problem, we know that he jumps 3 spaces. And so we're going to try and model this. And if I were in a classroom, I would have a little frog manipulative that I could actually use to model the jumps. Again, we want to make it as concrete as we can. What we're going to see here, though, is kind of a sketch level representation. So imagine, if you will, that this sketch represents an actual object. And that'll be closer in tone to what you'd be using in the actual classroom. So there goes Freddy. He jumps 3 spaces. And how many times does he do that? Well, he jumps 3 times. So before we get too far away, though, we need to build a record of this action. And the record of action that we're generating at this point, you notice, is tagged immediately. The shorter the distance in time, between action and record of action, the more meaningful the activity is going to be for the children. So we want to make sure that we tie in the record of action as quickly as possible. So there goes Freddie. He's going to jump again. And now he's jumped twice. By the way, you can have a little bit of fun with this. Freddie is so excited now that he only has one more time to jump. Watch what happens. Serious air. Did you notice that? Freddie got some serious air that time. And now we have each of our 3 jumps labeled. And the labeling is the record of action. Now, the final record of action is to show the total units in all. So when we see a number line representation, one possible record of action that we can generate is to show each of the 3 jumps and then to show how far that it results. It's a small step here to translate this over into do it dang it language, where we record the number of jumps, we record the distance each jump goes, we do it dang it, and we build meaning for the repeated jumps. What you will see here is you're going to see the same number of manipulative items being placed into a given number of placeholders. A typical example from the STAR test, for example, might be there are 4 balls in each of 3 boxes. How many balls are there in all? Well, let's see what that looks like. In the first box, we're going to have 4 balls. So there's the first, there's the second, there's the third. Knowing what you know about subtizing and chunking, anyone just think about where the 4th one should go? Yes, you're right. Left to right, top to bottom in subtizable and chunking units. And we really do want to be that consistent. Having spent all this time building this representation for what 4 looks like, we want to tap into that every time we have the opportunity. So we want to make sure that we don't lose out on that. And so now, of course, each of the other 4 balls are also going to be represented in terms of subtizing and chunking. And now the question is, how many balls are there in all? And one possible way of solving that problem right now could be to smush them together. It could be to do an ordinal count. It could be to do a cardinal count. You notice ordinal would be implying a left to right. Cardinal would be however we want to count them, but we do run the risk in cardinal counting of not counting everything or of counting some things more than once. Now, when we talk about the area model for multiplication, in this approach, you have a number of unit squares filling a rectangle of a given length and width, and then you count up the number of squares. And it turns out that the area is the associated multiplication problem. So let's say that we have a rectangle that is labeled here, and so we know that from here to here is 4 units, and from here to here is 6 units. At the abstract level, we would know then that 4 times 6 is 24. That's if you use multiplication as the definition for area. But we're going to do something different. We're using area to help define what multiplication is. And so what we need to do in this case is we actually need to show each of the unit squares. What this does is this gives us something to count. And so in looking at this, I now have something that's countable. I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 18, 24. I want to let you know there's a little secret behind how I did that counting. What we do when we count is we're trying to reinforce this notion of skip counting eventually, where we can say 6, 12, 18, 24. In initial instruction, though, what we can do is we first count everything with equal volume while we point to it directly. So we'll go 1, 2, 3, 4, 5, 6. For The next row that we would count, we count it softer with the exception of the last element. And we'll say that at full volume. So at this point, we'd say 7, 8, 9, 10, 11, 12. Now what we'll do is we will not count at all, but we'll still point to each one to kind of build that notion of internal counting if we need to. So in my mind, I'm thinking 13, 14, 15, but I'm not saying it out loud. 18. Every subsequent row now, we're going to reinforce skip counting. And so I will show by dragging my pointer across that that's what I'm counting, and then I'll say 18. I'm sorry, 24. My apologies. If we had another row, we'd say 30, 36, 42, and so on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18, 24. You may want to practice that. This is one of those teachable things that when you get used to doing it, it becomes natural. It's amazing how much this helps children remember what it is we're counting and build that relationship into the area model. Now, when we look at that, you notice we came up with 24 as our answer. This right here is not a bad record of action. All right, it's very reasonable. And again, we could put this into do it, dang it language fairly easily. All right, we could say, okay, we represent 4, represent 6. We have the do it, dang it line. And then we have what is it we're doing? We're building an area model. And again, we can use that as a way of getting into it. So, you know, if I wanted to put that forward for the little ones, this particular representation is not bad, and it makes a nice transition into flashcard form. Now, we're going to share a couple of reasons why these area models are the models of choice. In particular, I'll show you when we think our way through the multiplication by 15 example, the power that builds for visualization. But what it means is that since this is our best model, we may have to help children make the transition from other forms of multiplication representation. And it turns out that this is relatively easy to do. So let's take a look at repeated addition. First, what we will do is we will start off by having the number line that we used for the original problem. Then we're going to use unifix cubes that's the same size as the spaces between the numbers in the number line. Now, in most schools, one of the rulers that children will have centimeters on one side. You'll have the English units of inches, and then you'll also have the centimeters. And the beautiful thing about Dean's blocks is that each of the unit cubes is 1 centimeter. So if we're using a 1 centimeter ruler in terms of representing our number line, then the centimeter cube will fit right here. So one of the cubes would fit right in there. This is going to prove to be really helpful for us. If you think about the little snap cubes that I had where I could snap them together to build tens and some of those early examples, what we would now do is we'd represent the jumps on the number line using those snapping unifix cubes of different colors. So there's my first jump. And you notice I could represent that with the snap cubes. There would be my second jump. Again, I can represent that with the snap cubes, and then there's the third. Now, at this point, I have a physical object that I can organize. And so since I can organize it, I can maneuver it. And so we're going to rearrange these unifix cubes so that they join into an area model. And I hope you see how this can be done very, very easily. So we now see Freddy the Frog's problem as being able to be put into an area model that is 3 in one direction by 3 in the other direction. And if we want to practice how we would count that, we would count it 1, 2, 3, 4, 5, 6, 9. And hopefully that'll give you a chance to review a little bit on that recommended counting strategy. Again, I believe you'll find that's very, very helpful. Now, if we're going to transition from the stars and circles model, first, this is the representation that you might see in the Teach for America classroom, where you've got the circles on the board, and then each of these would be represented typically by a star or some other shape. You'll notice that I am taking the liberty here of organizing these into subtizable and chunking groups. You probably would not see that in a regular classroom unless the teacher is one of my former teacher candidates. And you know, it's entirely possible you might have your mentor teacher being someone who's had me or someone who's had an in-service from me. So if you do see it represented this way, you're kind of fortunate. Generally, the stars are just thrown in there, however. Now, what we're going to do here is we're going to join these Unifix cubes from each group. And again, I recommend using those little snapping cubes because it makes the actions a little easier. They are longer to snap together, but once you snap them together, they're a lot easier to manipulate because you can handle them and work with them as a group. Once you have each group lined up, you can arrange them into a rectangle. And I believe you can see now how we can use our emerging notions of multiplication to say this is 3 by 4, and we can use that to generate our multiplication. So we have a lot of ways now of transitioning from these other models. Now, it's important we recognize that division is best viewed as the creation of equal parts. And we're going to develop multiplication first, but I want you to make use of the area model for multiplication as a bridge to division. And this is one of the reasons why we stuck with the area model first. If the only way you have of viewing multiplication is as repeated addition on a number line, then the only way you have of viewing division is by repeated subtraction. And cognitively, that's crazy. I mean, that's not the way we address the problem. We address the problem by the creation of equal parts. And as we'll find, it's much easier to handle from the area model perspective. So let's look at our early model of 4 times 6 is equal to 24 and see what that looks like from this equal part perspective that we're trying to generate. So there's my 4 times 6 is 24. And remember what that tells us is it tells us that we're generating a rectangle that's 4 in one direction by 6 in the other. We do it, dang it. And when we do it, dang it, we count everything up. And when we count everything up, that'll give us our answer. So we came up with 24 as our answer when we did this before. Now, if we take the 24 squares and create 4 equal parts, that will mean there's going to be 6 squares in each part. Now, this is another way of representing division. Again, this symbol may not be the formal division symbol you might have expected to see, but it's a perfectly appropriate way of recording that action. And I'm tossing that up there just to kind of go back to Pon Ma Kettle for a moment. It's the concept of division, this creation of equal parts, can be recorded in a number of different ways. And historically, I think that's the point that causes confusion for a lot of young children. They see the division symbol represented in a number of different ways, and as a result of that, it causes them to focus on the symbol, like Zoltan would say, symbol shock, rather than the creation of the equal groups. And that's what I want us to focus on, to create 4 equal parts. So what that means is we're going to take these 24 squares and we're going to create 4 equal parts. And when we do that, we see that there are 6 squares in each of the 4 equal parts. So there's one part, there's the second part, there's one part, sorry, there's the second part, there's the third part, There's the fourth part. And you will notice now how we can see each of those 4 equal parts. Now, we can also take those 24 squares and we can create 6 equal parts. So let's see what happens when we do that. You notice that what we have now is we have 1, 2, 3, 4, 5. We have 6 equal groups. We can tell they're equal because they're all the same in terms of the number of cubes represented. And then when we figure out, well, how many are there in each group, there are 4 in each group. Now, at this point, we can go back and show how our view of multiplication is probably more robust than you might have thought about in terms of the area model. Because the initial area model not only shows that 4 times 6 is 24, but imagine that we rotate it now and make it look like this. It also shows that 6 times 4 is 24. The action we do here is a little different. It's more of an ordinality issue. Remember that now we're going to be counting in a different order. The cardinality is going to stay the same. It's going to stay the same at 24, but listen how we would count this in terms of our action. We go 1, 2, 3, 4, 5, 6, 7, 8, 12, 16, 20, 24. And so not only does it give us a chance to multiply count this, which is helpful, but it shows what happens when we build this rectangle. Instead of going this direction, imagine if we grab it and we rotate it. So if I have a tens unit, I could say that this is 1 in one direction by 10 in the other. When I rotate it by 90 degrees, it represents a different problem. It's now 10 in one direction by 1 in the other. And so this is building this notion that 3 times 4 is the same as 4 times 3. Kind of powerful. But remember, you have to teach both 3 times 4 and 4 times 3. Don't assume just because they know one, they're going to know the other. Now, when we put all this together, we can see that, first of all, 6 times 4 is 24. 4 times 6 is also 24. So you notice here's my 6 times 4, and here is 4 times 6. And when we count, all right, we have a different ordinal counting, although the cardinality is going to be the same at 24. And hope you see how these terminology is kind of helping us out here. In terms of order, up here, we're counting by groups of 4. In terms of ordinality down here, we're counting by groups of 6. And yet the cardinality, the how many, is still at 24. So it's kind of a nice way of looking at that. We also see that if we take 24 and we create 6 equal groups, we have 4 in each group. If we take 24 and we create 4 equal groups, we have 6 in each group. And look what we've got. We've got all of this showing up from a single picture. And so this is what's referred to as a fact family. And a couple of you have mentioned that, the addition subtraction, for example, sometimes they represent them as having the 3 numbers involved, and you look at all the possible ways they interact. Well, that's a fact family also. We can generate fact families in addition subtraction. We can also recognize and build fact families for multiplication and division. So when you hear the term fact family, whether it's in your curriculum guides in the schools you're in, or whether it's Van de Waal, or whether it's in your teacher preparation exams, it's going to be a biggie. It's going to be something that shows up. And basically, it shows that these operations are linked. Fact families will only work if you have inverse operations where one undoes the action of the other. And because multiplication and division are so tightly linked, we can show them all from a single representation. And this turns out to be a huge deal. We're going to be looking at addition and subtraction fact families. And we're going to show how unifix cubes and a number line can be used to generate addition and subtraction fact families, much in the same way that we saw how the area model for multiplication can be used to generate the multiplication division fact families. So let's look down here, and what we'll do is we'll notice that the problem we're going to be representing with the number line is 3 plus 6 equals 9. You'll also notice I'm using a slightly different representation than the objects now, and because I want to model as many different ways of showing addition for you as I can. So let's take a look at how we would model this. We'd start off by showing a unit of 3. We would then show an additional units of 6, and we could use those little snapping cubes to show how much it would be in all. And so we can now say that if we start with 3 and we add 6, we get 9. This would be the final record of action. So if we have a fact family, we should be able to make these 3 digits, 9, 6, and 3, show up as the record of action for each of those. See if you can follow along here and see if it makes sense for you as we represent some of these other problems. Here we have 6 plus 3 is equal to 9. And I'm going to be a little more obvious than what I probably would with the kids. I'll show the 6 right where we had it before. We have 6 plus 3 is 9. You notice same digits, same picture. Let's now take a look at the subtraction problem. 9 minus 3 is 6. We'll start with a 9. And so what we'll do is we'll visualize here this whole distance from here to here. We'll start with the 9, and then how will we show the removal of 3? Well, we'll just physically take the 3 out, and look what we have left. We have the 6. So again, very easy modeling, and the record of action that we get can be sent home for family support. That's what we're seeing down here. And it's concrete in terms of the objects we're acting on. Finally, for completeness, we'll take a look at 9 minus 6 is 3. I'm pretty sure you can see how we're going to do this. We'll take our full 9, and then we will remove the 6, and look what we have left. We have 3 left. So just as earlier we showed how we can generate these multiplication division fact families, it's also possible for us to generate addition subtraction fact families. And this is an extremely powerful unifying way of thinking about operations. It also, I think, helps explain why when I developed operations, I treated comparison as an operation, and then addition subtraction is sort of the first formal operation, even though typically it's taught addition first, then subtraction, as if they were separate ideas. I don't think that's a good idea, but I want you to be aware that's what you're probably going to see in the classrooms. And so in an ideal world, I think we should teach subtraction and then addition very, very quickly. We can use the questions of how much larger and how many in all to get at that. And when we do, we can tie those together as a single idea, you know, addition, subtraction. When we think of multiplication, division, by far and away, the area model is going to be the best. And in your classrooms, when you have students move in, maybe in mid-semester or sometime throughout the year, it's going to be worth your time to rebuild that understanding from the models they came in with to the area model for multiplication. In a supporting video, I'll show you how this area model links up to different types of multiplication, and I believe will totally make the case why this is such an important unifying idea.